All right, third question, how can we identify and organize elements, right? Atomic theory gets formalized in the 1800s, and it really gets fleshed out in the late 1800s, in the early 1900s with quantum mechanics. This identification and organization of elements is also an important prospect. And one of the major players in this was Dmitry Mendeleev. He was a Russian chemist, and he taught organic chemistry at a university in Russia, and he was trying to come up with basically a mnemonic device. There were a certain number of known elements, and he wanted his students to be able to memorize them all. And so he started making a list. And he listed the known elements in order of their mass at the time, but we found out later that the atomic number Z, which we'll get into later, shows repeating properties. So this atomic number, if you arrange it, you start to see repeating properties. Helium, with an atomic number of 2, acted very similar to neon with an atomic number of 10, and argon with an atomic number of 18. And so it started showing up that every 8 atomic numbers, you would see a repeating property. This was also known as the law of octaves. This was Humphrey Davy, an English scientist, that noticed that. And so what Mendeleev did was he started making a table from that. He started making columns. Anything that acted similarly went into a column. So all of the pink things that acted similarly were in one column, and all of the green things were in another column. And he found out that when he did that there were elements missing from the list of known elements. He said, well, if this one is the next one on my list, but it doesn't act like the ones in the column where I think it belongs, I'm going to leave a hole. I'm going to move it over to where I know that something, or where it acts similarly to that. And so these little elements in pink, purple here, scandium, gallium, and germanium, were actually elements that hadn't been discovered yet. Mendeleev left those holes and he said, you know what? They're going to show up. In fact, he called gallium eka aluminum, so proto-aluminum, or germanium was eka silicon. And so he said, you know, we're going to find them later. And sure enough, and he also said, you're going to find them and they're going to act like this. And sure enough, that's what happened. What I do want you to be able to know are the highlighted elements on the periodic table here, which is basically everything through about 85, really 88 radium. I'm not too concerned about the bottom elements here. And I do have some quiz links on D2L that you can quiz yourself with this. Now, there are some broader categorizations of the elements in those columns that I was showing you from Mendeleev's periodic table. Anything in the first 2 columns, except hydrogen, are the metals. Anything in the middle is called the transition metal, the low part of the periodic table. Then, if you draw a stair-step line underneath boron all the way down the periodic table, anything that touches that stair-step is called a metalloid, and anything on the right of that stair-step line are called nonmetals. We also have those inner transition metals, and that's an insertion into the periodic table. We pull them out and put them at the bottom because it would just make the periodic table too big to fit on really easy sheets of paper. When we break it down again and we go back to Mendeleev's classifications, anything in a column is called a group, and there are 4 groups that I want you to be aware of. The alkali metals, the alkaline earth metals, the halogens, and the noble gases. There are names for these other groups, but I'm not super worried about those at any given time. But a group is just a column on the periodic table. A period is a row. So these alkali metals, like lithium and sodium and potassium, rubidium, cesium, and francium, they're metals, right? What do we know? They're in group 1A. They're soft and shiny and low melting points. By the way, soft and shiny and low melting point is pretty common for any type of metal, not just the alkali metals. They're good conductors of heat and of electricity. And that's, again, a property of any metal, not just alkali metals. But one thing that's unique to the alkali metals is that they react very vigorously with water. And if you've ever been lucky enough to see your teacher put a block of sodium or a block of potassium into a glass of water, you know what I'm talking about. If you haven't seen that yet, just hang on. We'll be doing that in the lab. Now, the other thing about the alkali metals that's unique is that they don't exist in nature in their pure form. You don't find lithium in its neutral form. You don't find rubidium in its neutral form because they're so reactive. There's an awful lot of water in nature, and so they've really already done their reacting. They lose electrons in order to form compounds with other elements. What about in the next column over, 2A, alkaline earth metals? These are things like magnesium and beryllium and calcium, strontium, barium, and radium. They're shiny, and again, that's pretty normal for metals in general, not just the alkaline earth metals. This is unique to the alkaline earth metals. They do react with water, but they're a little bit more boring, and you'll see that later in the semester. And again, just like the alkali metals, they like to lose electrons to form compounds with other elements. And again, that's fairly typical of all metals, not just alkaline earth metals. The third group I want you to be aware of is the halogens. That's group 7A over on the other side of the periodic table, with fluorine, chlorine, bromine, iodine, and astatine. What's interesting about the halogens is that they act differently than the metals on the other side of the periodic table. They are very reactive, just like the alkali metals are reactive, except alkali metals like to lose electrons. Halogens really like to gain electrons when they form compounds. And the thing that's also cool about halogens, right, metals, the alkali earth metals, most metals on the periodic table are solids. But halogens come in all sorts of different forms. Chlorine gas in nature shows up as a gas. Bromine in nature is a liquid, and iodine in nature is a solid. And so you get a little bit more variety over on the non-metals side of the periodic table. One more set of properties to look at, and that's the noble gases, and that's helium, neon, argon, krypton, and xenon. That's group 8A, all the way over on the right side of the periodic table. These are chemically inert. They're non-reactive and pretty boring. You can make them react, but it's not an easy task. These are gases, and they're called the noble gases because they're unreactive, right? The noble gases were above it all. They weren't interested in doing that kind of reaction stuff. They were happy as they were. And we are going to find later in the semester that all of these things act the way they do because of their electrons. Metals like to lose electrons for specific reasons, and that's why metals act the way they do. Non-metals tend to like to gain electrons in chemical reactions or share them in chemical reactions, and that's why non-metals act the way they do. And so get used to the idea that the reactivity of an element comes from its electrons on the outside.